So, welcome to another exciting installment of Advanced Computer Architecture. As promised, what we're going to do today is talk about caches. So, caches are important. Let's look for a moment, just by way of introduction, at a die photograph of a Intel Skylake processor. So this is not quite this year's processor, but it's a classic desktop machine. And we're going to cover, during this course, pretty much all of the constituent parts of this machine. Over here we see the GPU, and we'll come to GPUs later in the course. Over here, well, we won't cover too much of the PCI interface and things like this, or the external interface to the main memory system. We'll see a little bit of that. But here we see the main processor cores, and this chip has 4 of them. They're connected via this ring interconnect thing here, and we'll see a bit more of that later in the course. And interspersed between the cores is what's called the level 3 cache. Level 3 because if we look inside, we'll see that this processor has more layers of cache, in particular a level 2 cache associated with each of the individual cores, and deeply embedded in the processor are level 1 data caches and level 1 instruction caches. So when we think about the pipeline that we were talking about in the previous lecture, and the mem stage of that pipeline, that mem stage basically accesses the L1 data cache, the instruction fetch phase, accesses the L1 instruction cache. And if you get cache hits in those caches, then the pipeline will proceed with the kind of performance that we were looking at in the previous lecture. So let's look at that. So as I told you at the end of the last lecture, we were looking at our 5-stage pipeline could go at something like 5 to even 9 gigahertz if you really push it. But that leaves us with incredibly little time for actually accessing the memory. Something like 5 to 8 gate delays. And if you think about the gates necessary to decode an address and index the appropriate part of a RAM array, and then select that the data from the RAM array, it's really not going to leave much time, and it's going to be extremely tightly constrained. So the magic trick, of course, is caches. Incidentally, caches, there was a time when they were not so important. In fact, and this is going to be a bit scary, I graduated in computer science from UCL in 1983. And this was kind of at the beginning of the phase when caches were important. Prior to that, the clock cycle time of a typical processor was not so different from the access time for quite large amounts of memory. And there were even processors prior to that where essentially all of the registers and all of the memory were in the same storage device. What we see is an enormous gap opening up between the access time of main memory, the DRAM that we use for gigabytes of memory in our processor, and the clock rate, the rate at which processors can operate. And although the access time for DRAMs has improved during this time, it has not kept up at all with the performance potential offered through Moore's law and increased clock rates and so on in the processor itself. So that brings us to this caching idea. It goes back a long way. The original caches were developed I think for the Atlas machine in the 60s. The idea is that we have a memory hierarchy, and it's a very familiar idea. You can imagine that you could do this with practical things like keeping books in a library and keep more frequently used books closer to where the users might need them or something like that. The cache is kind of the same. What we're going to do is fetch data from perhaps main memory and allocate it into a higher level cache memory in the hope that, in the expectation that, we might access that same data again, and then we won't have to go to the main memory. And obviously we have an issue with the limited capacity of this cache here. We might also think about the access time. We can think, in fact, of caches forming a big hierarchy. Many orders of magnitude separate registers, which you can think of as being explicitly managed scratch pad memory for operands that you might reuse. Level 1 cache, level 2 cache, level 3 cache. You can get processors these days with level 4 cache. Then we have our DRAM, our main memory. We might also have some kind of non-volatile memory in here. And then ultimately we might have a disk drive. And beyond that, we might even have, I don't know, something like a tape drive. I'll show you a bit about that later on. So what makes this trick work? Well, it's the principle of locality. Well, two principles of locality. And this is important. This is something I think I would really want you to take away from this lecture, is why do caches work, and the two different reasons why caches work. Temporal locality versus spatial locality. So temporal locality is where an item is referenced and that specific item will tend to be referenced again, right? In contrast, spatial locality is if a particular item is referenced, then it seems likely that an adjacent item will be referenced soon. And that's clearly different. It can also benefit from caching, because we could load a block of memory into the cache and then reuse successive elements of that block. Modern architectures are heavily reliant, almost totally reliant, on locality for performance. And that means as a programmer that locality is a fundamental consideration in algorithm design. So let's think about how to design a cache. Now, what I did with the 5-stage pipeline was I pulled the design out of the hat and said, look, here's an idea for how to do it. I'm going to do the same thing again. This time, I'm going to show you perhaps that this wasn't the greatest of ideas. So what I'm going to talk about here is a thing called a direct mapped cache. And consider for a moment a 1 kilobyte direct mapped cache with blocks that are 32 bytes wide. So 1 kilobyte, 1024, is 32 times 32. So we're going to have 32 of these 32 wide blocks. In the direct mapped cache, what we do is we take the address that the processor is trying to use and we pick out 5 bits, 5 because 2 to the power 5 is 32, and use those to index a particular row of this cache RAM. Right? This particular row contains 32 elements, right? It's 32 bytes. So the remaining 5 bits of your address here are actually going to be used to select which of those bytes the processor actually wanted. Now the thing is, of course, that we can allocate things into the cache, but we might need to check that in fact we've allocated, that the thing we're looking for is actually there. And that's the function of the tag section of the cache. So the tags are metadata, and they tell us whether we've got a cache hit or not. So it might be that a whole line, a whole row here is marked as invalid. The machine has just been turned on and none of the cache lines are valid. Or the last time we allocated into the cache, we allocated an address, we loaded an address from the processor, we allocated its data into the data part of the cache, and we allocated the remainder of the address bits into the tag part of the cache. Why? So that when we come later to access the cache, we can index, you can use the address bits, we can use these address bits from the address that we're looking for to search in the cache, to see, to index into the cache to see if that data is what we want. And we find out whether it's what we want by checking whether the tag matches. So there's a little bit of extra hardware really, isn't there? And what we're going to do is compare the tag that we get there with the address bits of the index of the requested address. And if those two match, then we know we've got a cache hit, provided of course that the valid bit was set. Meanwhile, in parallel, we can be fetching the data part, of the cache line, selecting which of the bytes we actually wanted using these low order bits, and passing those on to the processor. Happy? Right. What do you think of this design? Is it any good? It's cheap and nasty is what I'm going to show you. Let me show you why. Consider the whole of your main memory. So it's addressed 0, 1, 2, 3, up to 32, and then 33, 34, 35, and so on. Here's our cache. And remember that the cache is indexed with 5 bits from the address word. So, and the cache has a capacity of 1 kilobyte. So this yellow line here refers to data which will be allocated into the cache at this location in the cache data array. Right, so location 0, because it's address 0, but location 32 is also going to map to the same location, right, because we're only using 5 bits. These two green lines also map to the same location. And indeed, every 32 blocks in RAM share the same location in cache. So this is it a problem? I mean, the cache kind of works most of the time. Let's look at how this is going to play out in a particular program. And I've constructed a program here for you to illustrate how things could go badly. So imagine this little program that allocates 2 arrays, A and B, and they're each 256 ints long. And these are going to be allocated in adjacent memory, because that's what a compiler like a C compiler will do. Then we have a little loop nest that 10 times does this. And what does this do? It reads a segment, a 64-word segment of A and B, sums into R. And we're going to repeatedly sweep over 64 elements of these 2 arrays, sum the results into R, and do that again 10 times. Okay, so if we have a cache which is a kilobyte in size, like the one I showed you before, it should be fine, because look, the total amount of data that we need is 2 times the 64 ints that we need to store, and that comes to 512 bytes, easily fitting into our 1K byte cache. But what happens with the cache design that I've just shown you? So the storage layout is 256 words of A, here they are, and then 256 words of B, here they are. And 256 being a power of 2 is a multiple of 32. So locations A0 and B0, the first elements of the 2 arrays A and B, have identical address bits in those key 5 index bits that we use to index our direct mapped cache. That means that these 2 locations are going to map to the same place, like the yellow rows that I mentioned in the previous slide. In fact, not only do these 2 map to the same location, but these 2 map to the next location, but they both map to the same one. So in fact, what's going to happen is that our 64 ints are going to be allocated into a subset of the available cache memory, and we will leave much of our direct mapped cache unused. Instead, what happens is that we repeatedly displace each allocation. So we load this value into this cache, then we load this value into the cache, and displace the value we just loaded from A. We go around the loop again, we allocate this one, and then right away we displace it. So in fact the cache is really not being used at all. So this effect is called an associativity conflict. It's actually called an associativity conflict because it's fixed by a trick called an associative cache. Let's go back to the direct mapped cache picture that I showed you, and this is a slightly simplified version of it, but what we're going to do is take our address, a word, use the index bits from it to select a row, and then we're going to compare the tag part of the address with the tag that we got from the cache array to see whether we've got a hit. The idea of an associative cache is to do that in parallel in two halves. And in a moment I'll show you that you can do this with more than just two halves. So what we're going to do is use the same index bits to index into two separate direct map cache structures. And then we have two tags to compare, right? And our data might be in the left half of the cache, or the data we're looking for might in fact be in the right-hand half of the cache. We check by comparing the tag with the tag bits segment of the address of the read address with the tag that we got from the tag array. We check the same thing over here, and if either one of them comes out true, then we've got a hit. Whichever one does win determines which of the data values we actually get, right? So this multiplexer is controlled by the tag match outcome on the two sides, and whichever one does match is routed to the processor here. Of course, the processor can't use that data if it turns out that the hit bit is not true. Okay, so what do you think of that? This is called a two-way set associative cache. So there are some things to notice about this. One nice thing is, well, they're not necessarily nice things. There's a little bit of extra hardware just here, and in fact that hardware is not just extra transistors, it's also on the critical path for determining whether this data is usable. So that might slow us down. Remember, we only have 5 to 8 gate delays, and we've just used one of them here, or one or two of them here. Another thing to think about is that you might actually discover whether you've got a hit after the data becomes available. We also need more comparators, so we do need more transistors. So let's look at a concrete example. The Intel Pentium 4 processor, the version of the processor we're talking about here, they had an 8K byte cache. Each block was 64 bytes, not 32 bytes. 32 bytes as I used in my diagrams earlier. The cache has 4 ways. So it's not just a two-way set associative cache as shown in this diagram, it's a 4-way set associative cache. Each of the, so each RAM array holds 32 blocks. So again, you use 5 bits to index the cache. The tags then, because it's a 32-bit processor, the tags end up being 21 bits long because we've got 32 bits, but we take off 5 for the index because we don't need to use the index bits in the tag, because we know what they are based upon where we found the tag in the cache. And then we also subtract off 6 bits because of the 64-byte cache line size. So each of these cache lines holds 64 bytes, and those 6 low-order bits will be used to select the particular word that the processor is accessing. Okay, so that's the fundamentals of caches. What I'm going to do is review a number of introduce you to a number of fundamental issues in cache architecture. Block placement, block identification, block replacement, and write strategy. Let's go straight into this block placement question. Where can a block be placed in the upper level, in the cache that we're looking at? And so the direct mapped cache that I showed you, there's only one place where data can be. Based upon its address, you can determine exactly where the data will be if it is present. And then you can check its tag and you're fine. The trouble with that is the associativity conflicts problem that I mentioned to you. The two-way set associative cache idea says let's divide our cache into 2 halves, index them both at the same time, and now we have 2 places to look. Our data might be on the left and it might be on the right, and obviously we could do this 4-way as the Intel Prescott cache did, or even more. In fact, hey, why not go extreme? Why not keep on dividing the cache until you index, or until you access all of the cache lines, the cache blocks in the cache at the same time, and you do a tag comparison for every block in the cache. This is called a fully associative cache. It has the advantage that a block can be placed literally anywhere in the cache. It has the disadvantage that, of course, we need many comparators, one for each block, and it may therefore use more transistors and more energy as well. It does have an advantage in terms of cache hit rate, though we will see some statistics later on that show that that the returns diminish after a while. A little bit of associativity helps a lot. A lot of associativity doesn't help quite so much. What it does do is make your program more predictable. So what's really horrible about the associativity conflicts that you see with a direct mapped cache is that although most of the time luck is on your side, occasionally your data just aligns in a bad way, and 2 data structures that you need to be in the cache at the same time have addresses which mean that they can't be. And that's very unfortunate, right? That means your program will be systematically slow due to associativity conflicts. A fully associative cache has no such problem with that. The cache hits that you get are completely independent of the storage layout. And that's a very nice property. We'll come back to that later on too, of course, because there are other ways to try and get that property too. You might comment incidentally that when I introduced caches to you, I said, look, cache, what you do, you allocate stuff that you've recently accessed into the cache, and if it's there when you index again, then you get lucky. And so the direct map cache is a pretty cheap and dirty solution to that problem. All it does is it works. It uses the direct mapped cache is cheap and simple, but it doesn't properly fulfill the wish that you had to be able to allocate any address without prejudice. The next question to think about in the architecture of any cache system is how do we actually find the data and how do we allocate? So we have, in addition to the memory necessary to store cached data, we have memory dedicated to holding the tags associated with that data to tell us whether we've got a cache hit. And you might ask, how big do these tags have to be? Well, they have to be big enough to hold the address bits that we need. The address bits that we need are not the block offset, the bits that tell you which byte or which word within the cache line you're actually accessing. We also don't need the tags to include the index that was used to select the set here. So it's the two-way set associative cache. This is away, and this is one set indexed with a particular cache index. The index selects which set we're in, and those bits don't need to be part of the tag. So as the associativity is increased, we use fewer bits. If we keep the cache size the same, if we increase the associativity, we're dividing the cache into more parallel chunks, and we're using fewer index bits to index those parallel chunks. And consequently, we need to use more tag bits in the tag array. Of course, another way to reduce the overhead associated with designing a cache is to use larger cache blocks. So if we use 32 bytes here, then the amount of tag memory overhead per cached item gets proportionately smaller. The next question to think about is what about replacements in a two-way or more in an associative cache design? So in direct mapped, there's no choice. There's only one place to put an item. So when you load something from memory and you decide to allocate it into the cache, then it must displace the one thing in the cache that is currently occupying that space. In a two-way set associative cache, we actually have a choice, and we could look at those two cached data values and ask which of these is less likely to be used in the future. Well, wouldn't it be wonderful if we knew what was going to happen in the future? If you've studied operating systems, you'll know that paging algorithms and so on have the same problem and for the same reasons. What you could do is use this least recently used strategy. Least recently used is a kind of mirror of what would actually be an optimum strategy. Least recently used would be, the ideal strategy would be least soon reused, right? So if you've got two values in the cache and you're forced to displace one of them, let's displace the one that will be which will be accessed in the most distant future. Least recently used kind of assumes that the future is going to be similar to the past. Least recently used is a little tricky to implement. You need to keep track of which of the ways were more or less recently accessed. And there are some nice hardware tricks to do that. We don't have time for them here. But there's a little bit of hardware overhead associated with keeping track of which is the least recently used. Turns out that actually it doesn't make that much difference whether you calculate carefully and use the least recently used strategy, or you simply evict things at random. You toss a coin as to which one should be evicted. Let me just show you this random benchmark study taken from the textbook from a few years ago. And what they did was they took a standard benchmark workload and evaluated the cache miss rate on caches of increasing size and with increasing associativity. So over here we have the biggest cache with the highest associativity, and it has a low cache miss rate. And here we have the smallest cache with the lowest type associativity, and it has a rather poor miss rate. What we see is that for the very small cache, LRU is a bit better than a random replacement strategy. But that difference becomes really insignificant as the cache gets bigger. And in fact, when we look at more associative caches, the difference really disappears quite quickly. Now, this is all to do with average programs. And you might wonder, well, perhaps there are particular programs that would benefit from LRU. And there probably are. But another thing to think about is that there are programs which behave pathologically badly with LRU. So a program which repeatedly sweeps over an array that doesn't quite fit in the cache would be a particularly poor program with LRU, because the least recently used data is in fact what you're going to access quite soon. The fourth question that I thought I would introduce you to in this lecture was this choice, and there are quite a lot of kind of policy choices with caches. And here's one. What happens when you have a store instruction? Basically, the processor issues a store instruction. We clearly have to look in the cache to see if we've got a cached copy of that data. If the cached copy is present, we must update it. If it is present, do we also have to update the next level of the memory hierarchy, or the main memory? And the write-through strategy, WT, the write-through strategy, is the strategy that you always update both the block in the cache and you propagate the write to the next level of the memory hierarchy. In contrast, the write-back strategy is where you update your cached copy, but you don't tell anybody else about it. You don't tell the next level of the memory hierarchy about it. You will eventually have to propagate that write to main memory. For example, if this particular cache line is evicted, if it's displaced due to an allocation of some other data, then at that point we must write the data back. So the write back strategy depends upon having an extra status bit associated with each cache line to tell you whether it's clean or dirty, whether it has been updated or not. And if you displace a cache line that has been marked as dirty, then before you can use it, you must write that data out. Okay, now write back sounds a little more complicated to implement, and it is, but you might wonder what the trade-offs between these two strategies are. One simple one is, let's look at this one because it's a big one. The write back strategies has a huge advantage in that if you repeatedly write to the same address, then clearly the write back strategy absorbs those writes, executes them on the cached data, but doesn't have to propagate the writes to the next level of memory hierarchy. And that can be a big energy advantage because the less activity in the lower levels of the memory hierarchy. It might in fact be a performance issue because the next level of the memory hierarchy might actually not have sufficient bandwidth. It might back up, it might block you might as a consequence get blocked by those writes. You can use a write back buffer, a queue at that point, to try and mitigate that problem. But the write back solution avoids that particular pathological case where we repeatedly write to the same location. In fact, it's even better than that, because if you have like a 64-byte, 8-word vector cache line, we might not be repeatedly accessing the same line. We might instead be updating successive words of an array. And the write back strategy lets you write all of the words of a cache block into the cache line before actually propagating it to the next level of memory hierarchy. Of course, right through seems reassuring because it means that the rest of the memory system more promptly gets up-to-date data. That is something we will cover in much more detail later in the course. It's the cache coherency problem. The most important thing, though, is that right through doesn't solve the cache coherency problem. I wonder if you can see why. So the right-through strategy, it does propagate newly written data to main memory. And that's great. Now the main memory is up to date. But if you have other processes in the system, all trying to access the same addresses, propagating the data to the main memory isn't actually enough, because those other processes may have got cached copies of their own of that data. If they've got cached copies, then they will continue using those cached copies. And just because the main memory has been updated doesn't help you. In fact, what we need to do is to somehow send the other processes a message saying, hey, this data has changed. And that we will come to later in the course. Okay, so caches are a huge topic, and we will dive in more detail into this huge topic shortly. And we'll talk a little bit about, much later in the course actually, about cache coherency, that very problem. If you have multiple processes in a system or multiple caches, how do you keep them consistent? I'll show you various tricks like victim caches and prefetching and so on, and actually many more. We'll look at multiple levels of caching, for example. I thought I'd finish today's lecture by just talking about what happens at the very bottom of the memory hierarchy. And this is, I thought I'd mention it because it's something you don't see very often. These days, your desktop computer has registers, level 1, level 2, level 3 cache, and then perhaps an SSD, and that's it. If you've got a very large system, you might have some hard drives. If you're in the business of looking after really large amounts of data, then hard drives are going to become an expensive and unattractive option. If you're Facebook and you're in the business of storing everybody's photos, the social lives of all of your customers, if you're providing an email service and you need to commit to your customers that you will retain historical emails for them, or if you're working in banking and you need to keep long-term histories of financial transactions, all of those cases, and of course, big science. So I show you a picture of this one just because it looks awesome, and I've actually seen one. It was at San Diego Supercomputer Center, and it was being used for storing the results of massive computational simulations, each one of them costing a huge amount to execute, and so they wanted to stash the results in case they needed them later. Similar systems are used, for example, for storing images from space telescopes and things like this, or from large physics experiments. This is a slightly more modern version of the same thing. What's happening inside these devices is a lot of shelves, and each shelf, not all of these shelves are occupied in this picture, each shelf holds a tape cartridge. And moving rapidly up and down, this is this device here, you can't quite see it. This is a fast-moving robot tape delivery mechanism. What it does is it goes to a shelf, grabs a tape drive, moves it to, grabs a tape cartridge, moves it to the tape drive, and keeps a number of tape drives busy with accessing different tapes. Here's the inside of the powder horn device, the big round circular thing that I showed you. And it's kind of similar, but slightly more visible. That's the bottom of the memory hierarchy. Let me show you another thing, also actually from San Diego Supercomputer Center from a few years ago. It is possible to build machines that don't rely upon caches, and therefore don't depend upon locality in the access pattern of the memory accesses. The way you do it is embodied by this radical architecture, and there are successors that I'll tell you about later in the course. But in this machine, I'm just showing you this because it's a cute design. It's not a very beautiful thing. The one I saw was actually disappointingly mostly empty as well. But what they did was they built a massive parallel memory system, a very fast interconnection network connecting all the processors to all of the memory units, and then each processor was multiplexed between 128 different threads executing in a round-robin sequence. So each thread would execute, perhaps issue a memory load, and then the processor would execute similar instructions from 127 other threads before coming round to this thread again, to the instruction which is going to use the result of that load. And the memory system was designed to deliver with high probability any accessed data value within 128 of these cycles. So essentially in this machine, there is no need for any data cache whatsoever. And instead, memory access appears to be completely uniform for all threads. What the designers of this machine liked to say was that their objective in designing this machine was to make the performance programming manual for this thing thinner. The performance programming manual for your favorite Intel processor is really rather thick document, many, many hundreds of pages. This one, they tried to make it a lot thinner. Essentially, the recipe is have enough threads. And with enough threads, you can hide the memory latency. What do you think? I can't tell you it was a successful product, but it's not such a crazy idea. It's an unattractive idea if your primary concern is energy, because of course every memory access involves crossing the interconnection network, activating a remote memory unit, and so on. However, we do see similar ideas, particularly in graphics processors, which we'll come to later in the course. So that brings us to summarize today's lecture. Without caches, we really would be in trouble. DRAM access times are commonly hundreds of clock cycles. And so as that gap between DRAM latency and processor clock rates, as that gap has increased, we have introduced caches, and then 2 levels of caches and 3 levels of caches, and perhaps 4. One of the things we haven't talked about in today's lecture is memory parallelism. So one of the things you might hope for, of course, is to execute multiple threads in parallel on the processor. You might also hope to execute multiple loads and stores in parallel with each other in the memory system. And one of the issues and things to look out for in the later lectures of this course is the various different mechanisms you might imagine for keeping parallelism happening in your memory system. I mentioned that, of course, caches fundamentally depend upon spatial and temporal locality. What this means is that if your programs don't have spatial and temporal locality, then your performance could be dominated by the DRAM access time, not the clock rate of your processor or the performance of your caches. And there are programs that really do this. Any program which accesses random addresses, like a hash table, is doing really, really expensive things. I talked about direct mapped caches. They have some performance advantages. Set associative caches, including fully associative caches, overcome the associativity conflict problem that I mentioned. And I gave you a little taster of what we might call the policy questions. And we'll see many more of these actually, but in particular we'll see more of these when we look at cache coherency protocols for multi-core systems. Okay, next stop is a discussion exercise on what I call the Turing tax. I hope you enjoy that. And then we will dive deeper into caches and the memory hierarchy. Thank you very much indeed. See you next time.